Record. Okay, so we're going to start a new chapter on combined stress, as I said, and one of the example from this chapter illustrating combined stresses, that is bending and torsion, and that happens like at the this location on this L piece. So really you have an L-shaped beam. This is horizontal, this is horizontal, that is fixed into a vertical wall. And probably intuition tells you that if any failures to occur will be occurring at the support. Okay. So this horizontal length A portion of the beam is going to bend as if it were encastrated. And then this other one is going to bend because of, likewise, it's encastrated, it's loaded with a force P that you assume it's applied here. But in addition, because I shift the force along the vertical axis through the horizontal or the longitudinal axis through the beam, is going to also twist the bar. So we have two effects upon this piece, the cantilever. We have the twist and we have the bending. The twist, that is the shear stress caused by torsion, is going to be the same throughout. You know that, well, things happen here at the bend, but we ignore that for now. And so torsion stress is shear stress due to torsion is the same anywhere. And then you have maximum bending stress, like in a encastrated beam that happens, you know this very well now, it happens right at the encastration. So if you take a bar and you clamp it in the vise and you pull, the maximum bend will happen right where that bar or rod comes out of the vise. Okay. But I said I want to get with you to go and analyze deflection. What would be the drop of point D where the load is applied? And you'll see we can use what we've learned so far. We can use principle of superposition. I need to raise this screen, or this screen. And so let's see how we can proceed. I have some, let's see. I have some values to consider for this stress bar. Again, figure is on page 558, and I assumed a distance B of 300 millimeters, a diameter of 30 millimeters. So this is 30 millimeters. This distance B, 300. And then distance A, 150. Okay. And then the material, it's has Young's modulus of, I took 200 gigapascals and shear modulus, so E 200 gigapascals, and for torsional deflection we need this information, 80 gigapascals. Okay. And I have here, although it's not round, but I have a demo piece that can illustrate what's happening. So I said, we saw this before. If you're to analyze this beam, you separate the A length portion from the B length portion, and figure out what is the interfacing, internal reactions where you separate the two. We've done this before. So I go a little bit against the notations in the book when it comes to the axis in this system. So you like to have the x-axis along the beam, and that's why I chose x going in this direction rather than the book's choice for, if you look at the companion figure. And then I want to have a right right-hand frame. So how do you, if I have an XYZ frame, X and Y, Z is up and makes for a right-hand reference frame, because if I rotate X towards Y on the shortest path, a right-hand screw will come out and in the direction of Z, okay? So if I have a right-hand screw and I rotate it as I move from X towards Y, it will unscrew and move up. Agree? You know, this is how you unscrew. This is how you screw. You fix something under the sink, but you have your fingers trained. And anyway, so yeah, Z has to be up and Y is going to be in this direction. So this is Y. And Z up, I need the, hey, you're late. But we discussed the solutions. You're not on camera. This is your paper. Check with colleagues. So yeah, I'm going to, I'm not going to do this too often. So Z axis, okay? And I said that we can, for stress analysis, we isolate the B length piece and then we isolate the A length piece. We have the load P, and this is like being, you assume this to be like a supported beam, incastrated beam. So I need to show load reaction at, never label these, I can call this also, but A and B, and this is point C, okay? So I have C in point B, and this is reaction at B, okay? And then I also have to show a moment, because again, this is like being incastrated, so I need to show a moment that goes about the, if I'm to extend, use the same notation. So this is going to be the y-axis, this is going to be x-axis, x-axis, and this is y-axis, and this is z-axis, okay? So I need now to transplant, this will be moment, it's about x-axis at B, and I need to not transplant, but rather show them as pairs, action and reaction. So I take the RB force and show it here. And of course, RB force is nothing but P. I can call this P right away. And then there's a moment. So moment acts, maybe it's a better, it could be better represented as such. So moment XB, it's actually is not well oriented. This should be the other way. So I showed the negative of XB here, MXB, which is nothing but P times A. Is that correct? So this portion of the beam is going to be subject to bending like a incastrated beam, right? So just the A length, I'm assuming is to be incastrated, you clamp here, and under the effect of force P, it just bends like an incastrated beam. Make sense? However, I have a support here at A. So my force at P, what it does, it's if I slide it, translate it at point B, is going to bend the B length beam, but in addition is going to, because of this moment or because of this offset, is going to twist the beam. Does it make sense? Okay, so this justifies the loading that you can see here. So it's essentially I have a torsional stress that's acting or caused by the PA moment, and I have bending like in an incastrated beam due to the force P being at distance B. Okay, everybody clear with this? All right, so we can tell the stresses on the beam. We care mostly about the tensile stresses due to bending rather than compressive stresses. So they're going to be maximum, and here's where it's nice. It's good to have a nice figure and trying to get that just that. So talking stresses now, but I'll come back to the challenge of finding really how much this load P will or point C will drop, and I assume a force of 1,500 newtons for P. So this is 1,500 newtons. So question is, how much will this point C go down? That's our question. So how much is this drop? You know, have I used the notation for it? Well, we can call it X total. Actually, no, it's a Z, delta Z total. All right. Let's see, would have helped to have it as, usually have X, Y. If I have X, Y, this was my choice for axis. We usually see Y as a deflection. Anyway, so regarding stresses, I said that along this beam I have torsional shear stress, or shear stress caused by torsion, and it's the same throughout. The stress distribution on any cross section, including one here that overlaps with maximum bending stress, if I take a section and we looked at it, this one here, I see the shear stress caused by torsion. Now question is, which one is towards us if I make a cut, or the one that's left? And I'm talking about the one that's left. So the one that's left is going to be sheared in this radial distribution that we know. So, okay, anywhere I have maximum shear stress that is tangent to the outer skin, it goes to 0 to the centroid. Okay, how big is this stress? Tau. Again, we use tau notation for shear stress. I've seen students using tau for any stress. It's not like so. We distinguish between shear stress and tensile compressive stress by using separate symbols. Their effects are different. Shear stress and tensile compressive stress are not the same. The material responds differently to the two stresses. You can get their equivalent, going between shear and tensile. Yes, we'll learn this in today, but we use different symbols. And the response of the material is also different. So you have torsion, and it causes rotation, twist. And you have tensile compression, which causes stretch or bending. So stretch, tensile stress, compressive stress, well, it starts buckling. And when I do bending, I have tensile above, compressive below. You need to visualize these because we're going to delimit what's called a stress element. So this stress pattern due to the torsion, the twisting, happens anywhere, including here at the encastration, where bending stress is maximum. Okay? So I'm going to delimit, and let me use color. I'm going to delimit this element that is one coming right out of where z-axis comes right out of it. Okay? Why is that? Because there's where I have the maximum bending stress that is tensile, which is worse than the compressive stress. Okay? You can take a short cylinder, a coin, and you can build a second empire building on top of it, and like what? Maybe we'll get a little bit thinner, maybe, or flatten, but nothing will happen. If conversely, of course, you need to have a little bit longer to where it can pull it. It can separate it. Of course, if it's brittle, it can crumble. All right? And that's when building was like masonry with bricks or with rock, with stones. You limit the amount of compressive stresses. But for ductile material, you can make it like aluminum, the thickness of foil, aluminum foil. Anyway, so back to our problem. We have this beam, and as I bend it down, maximum tensile stress will be on top, maximum compressive below. Now, if I take this element, I look from it from above. I take it and draw it here. Right? I look to the element, and the element, actually, it's a little cube or a little parallelepiped, a little box. And I need to, I align it for convenience with an axis, like longitudinal axis is the x-axis, is almost a rule. Okay? And I have the x-axis, and I have the y-axis. If you look from above, the right way, actually you need to be above and behind. So you have your eye looking in, your nose is here, and you're smiling. Well, nose. So you look from above. The z-axis comes through your eye. You see x-axis to your right, actually this is the way, So y-axis away from you, x-axis to your right, and I can start showing the stresses occurring on that element. Is there anything that happens along the z-axis? Question. Along the z-axis. I'm on the outer skin, z-axis. Z-axis is free surface. There's the atmospheric pressure. Nothing happens. If you drop this thing on the bottom of the Mariana Trench, where the depth of water, not even, you can do it in somewhere location Gulf of Mexico. You will have pressure acting like hydrostatic pressure, but it's not our case here. So that's zero stress. However, we see in the x direction, we see the stress caused by bending. And of course, if I isolate the P, so this is sigma, and it's in the x direction. And if I isolate the cube has to be in equilibrium, so I need to show another sigma. Okay. Anything happens along those, and I can show them on the stress element. So sigma x. Anything in the y direction? No, nothing. Should be, is not. It can happen. There's a chapter, I think it's 13 or 12, chapter 12, that discusses pressure vessels. Maybe I should run quickly over it. So if you have a pipe that is pressurized, of course, it has to be capped, to hold that pressure. So if you have a pipe that's pressurized, the pipe has the tendency to stretch and also expand diameter, right? You can, you buy those shaping balloons, they're long, and you make them into donkeys. And so if you inflate them, they elongate, but also increase diameter. So in that instance, if this were pressurized, I have, in addition to the stress caused by bending, that longitudinal stress, and then the hoop stress, it's called. So there will be a stress in the y direction, the one that's responsible for increasing the diameter. Not our case here. And now let's look at the stress caused by shear, tau. So the stress caused by shear, this is where visualizing was a little bit of like intuition, seeing in 3D, whatever, comes helpful. So if I make a cut over this surface, not the back surface, and I see the rest of, hold the rest of the bar from twisting in the direction of M, I see a rubbing going in this direction. Do you agree? Or if you think of the element, you look at the element from, maybe it's best you just show it. I take it, represent it here. As the bar twists, this turns into, this is how it deformates. Is that correct? In order for a stress element to deformate due to shear from this arrangement to this arrangement, this is like perspective view. I maintain the same. Otherwise, looking here, the stress, and don't forget, we rotated the element. So the element that is stressed by shear is going to be what? So I'm looking at, this is this corner here is going to be this corner here. So if I call this corner Q, am I right about this? First time I'm doing this. This rubbing, it's enough for me. And you have two clocks. You don't know the time. If you have one, or you're never certain. So if I look from above, actually no. If I look from above in the x-axis and y-axis, what I labeled as Q is actually this one here. Okay, so where is this corner going as the twist happens? This corner is going to, so I've got it. It was this one, it was here. So what it went like something like this. Again, this first time I'm doing this. Rubbing was okay. For years, I just explained students, imagine make a cut. Imagine the rest of the bar rubbing against. So my palm is this surface. And as I twist it in this direction, I rub this way. And that's the way the shear stress would look like. And this is tau intersects x is in the direction of y. And that's it. But now I'm trying to match it with the way the element deflects. I'm above, I'm looking at the element, okay? And as the torque acts, you know, I have a deflection that turns a rectangle into a diamond. Okay, and it's one thing to for diamond go this way, and it's another thing to go the other way. So can we match that diamond with the original rectangle? And I said, let's identify a corner here. Don't forget, we took the element and now curves rotate with x-axis to a right, y above. So I'm still looking from above through the x-axis. And I see what? I see Q in the second quadrant. Where is this point Q going? And actually, I may need to amend my drawing here. So I'm confusing students by introducing stuff that I haven't practiced. Okay, so where is this corner going as the bar twists? So that corner is going to go inwards. So actually that becomes clear once I approach the problem from the right end, begin with the answer. So this, under the effect of these shear stresses, the diamond is going to squeeze this way. This is actually going to move inwards. This is going to move outwards. Okay? But let's stay with the rubbing. I liked it much better. So just assume that you make a cut in your palm is this surface. And you see the rest of the bar rubbing your palm. And you can tell the stress that it intersects the x-axis in the direction of y. So I start with tau xy. This will be the starter stress, tau xy. And if I know one of them, I can complete the element because they are head to head, tail to tail. Okay, so once I have one, and this is called tau xy, then I can represent the other ones. So let's forget about where the corners go. You can use that if you're more comfortable with it, but I'm going back to charted ground. So again, I identify tau xy, and I know the stresses go head to head, tail to tail, head, tail, head, tail. This is going to be, so it's tau xy because intersects the x-axis in the direction of y. This is going to be tau. It's in direction of, it cuts rather y in direction of x. It's tau xy again, and this is tau yx. Okay? If you're to sign shear stress, you give them a sign based on which direction they tend to rotate the element. So tau xy, these two tend to rotate the element counterclockwise. These two tend to rotate the element the other way. In response, the element is not rotating, but rather squishing from rectangle. It goes to diamond. So under the effect of the stresses they are shown, the element is going to go this way. Okay? And we saw this when discussing deformation due to torsion. So all the elements deforming this way built up, so there's an angle gamma, and this angle gamma is, it's cumulated until we get the angle of twist theta at the end of the bar, remember? So we had the angle of twist formula. Let me complete these equations. So maximum shear stress is going to be T over J times C. C is going to be So I have T times diameter over 2. Sigma is M times diameter over 2. Outer diameter, and I, area moment of inertia. And then we have the angle of twist. The angle of twist is what? L times, what was it? L times T over shear modulus over J. This is the angle of twist formula. It was in chapter 2. What equation was it? Yeah, I have it written somewhere. So to page 244, I think it is, was when it was first introduced. Okay. So angle of twist, it's the combined deformation due to shear that builds up and results in a rotation of one end relative to the other one. Okay? Questions? Yes. So T from here is nothing but P times A or MB. This is P times A. And likewise here. So P times A. And then for what is M? M is going to be P times B, and I can call it My. Because of the incastration, it's like having the beam subject to, I need to shift this force right here at the z-axis, but because I move it the distance b, I need to introduce a moment. So yeah, if I'm to draw the free body diagram of just the stub of the bar, neglecting its thickness, so I need to introduce the shear force, or P, which would be the shear force, and I introduce a moment that is going to be M about this was X, Z, and Y, so it'll be My, M in the direction of Y, and it's going to be P times distance B. That's the bending moment. But now we're on 3D, a little bit more complicated. We need to, carry these moments with us or label them in a helpful way. Is it clear so far what we were doing? Okay, so I have bending stresses combined with shear stresses caused by torsion. This is very common in both in structures and in machine design. You have a shaft that transmits power, so it has a torque to it. And then you have either gearing forces or tension and belts forces or chain forces that add bending to that shear. Okay. Don't forget again that the shear stress is the same. It goes like in circle, in circle, circle, 0 at the center. Bending is maximum for positive moment. Actually, no, why I say positive? For negative bending moment is maximum on top, tensile maximum compressive below. Tensile stresses are more severe, have more severe effect than the compressive stresses. And you can have, I have a preference you'll see in design machine elements of taking realistic cases where there's pressurized pipes to which either during assembly or servicing you add bending. They can bend, you have long pipes pressurized and under the effect of their own weight, you can have bending stress. And you shouldn't neglect those to be on the, on the safe side. And then you can have torsion that you can induce either this way, you have an L pipe, or maybe you have a wrench that you tighten you have a cylinder full of, full pressure oxygen, and you tighten, you do with a wrench, you tighten some nut, some connector, and you add to the stress. Of course, it's designed where nothing happens, but why not do verification of the combined effects? Okay, so question, what happens now? I have on the same spot, I have a combination of shear stress and tensile stress caused by bending. Again, I can have in addition, I can have a force that in addition is causing tension. So if I take this force and rotate it at some angle, Actually, I do two things. I bend the piece both down and backwards. And in addition, I have tensile stress through the pipe, through the section B of the pipe. Does it make sense? So if you look at this one, okay, I have a down force with the bending and everything and torsion. But if I have another force that's pulling towards me, I do another bending in the different plane. And I also drag, now it has the tendency to come out from the wall, right? So there will be, in addition to the stress caused by bending, I'll have a stress that is direct tensile stress, okay? Those are easier cases because if I have direct tension, I just add them to the bending stress. The bending stress distribution, if you remember, it's of this type for a round or I-beam symmetric section. Maximum compressive goes 0 at the neutral axis, maximum tensile goes 0 to the neutral axis. And if on top I'm adding a tensile stress, which is even throughout, I'm going to magnify the tensile stress by this amount, and I'm going to diminish the compressive stress by this amount. So this results in a stress distribution that is more tensile, less compressive. By what amount? Well, I can just, and of course the neutral axis is shifted. So this was sigma due to bending. This is sigma due to force. Yeah, sigma due to moment plus sigma due to force. Yeah, sigma due to moment, which is -1, plus sigma due to force, the positive one. Does it make sense? Those are easy. Okay, so I'll go back to the question that asked, how we're going to account for this combined effect. So there were called theory of failures, and there's one that is listed here. So maximum shear stress theory of failure. And you can calculate an equivalent tau max by taking square root of the tensile stress sigma over 2 squared plus tau squared, likewise. So for our problem where I have sigma x and tau xy, this is how I get the equivalent shear stress. And there are materials which fail when their shear strength limit is achieved. I can Google, I know there are a few that come up. So I need to lower the screen. I'm going to Chrome. If I'm in Chrome, I cannot log into Blackboard without the Duo, but it looks like they favor Microsoft tools. So let's see. Brittle material failure. I look at some images and okay, have tensile in compression, failure in compression. Okay, so this is a drawing, but I want to show actual actual specimens. So yeah, this is a nice one, which shows, or maybe here. All right, so these are brittle materials like rock, salt, concrete, and you compress them, and you can see they slip. Well, it appears to be a pre-existing orientation in the rock, but it fails at 45 degrees for some reason. And you can see this with iron. See the 45-degree fracture? So that happened because for that particular material, it was exceeded the maximum shear strength, and it failed accordingly. The stress was longitudinal. You know, how comes you press longitudinally, but it fails at 45? Okay. And it has to do, again, with the behavior of certain brittle materials. And there are iron and cast aluminums that behave this way. It's not the only theory of failure. There are others. For ductile material,
There's one that capture, this is more conservative if you're applying to ductile material, but it's maximum distortion or distortion energy theory due to von Mises. And if you played with a final element package, maybe you remember von Mises stress, the equivalent stress, which is by default. And students tend to, or users tend to use it for any material, plastic, 3D printed material, they use von Mises stress. That's not correct. The material has to be homogeneous and ductile, which is not a case of wood, of concrete, I've seen wood analyzed in reporting von Mises stress. Anyway, but this is the one that's introduced in this book, pages 597. Okay, 597, I said. Okay, so maximum shear stress theory of failure. You can calculate an equivalent shear stress, and you compare it with the tensile strength in shear for that material, and you report failure, or if it's acceptable, if design factor is 2 or above, depending on the the way you want to report your analysis in terms of limiting load or maybe design factor. In terms of stresses that are just in alignment, and these are called principal stress. If I don't have any shear, that's called principal stress. Okay, so I gave you the example of bending stress and direct tensile stress and how the end stress is evaluated. The more complicated cases are, again, those where I have tensile, compressive, and shear stresses as they occur when you have torque transmitted on shafts again. And the way we look at these problems really is by taking that element, the stress element, and you saw we align it in a convenient way. We align it with the with x-axis, the longitudinal axis of the part. So you had a pipe and you put it along, in line with the pipe. You don't put it in a random orientation. Why is that? In order to like what? Maybe you build a building, or you take north-south as a direction because that's a very good reference, and then relative to the north-south line, you say, yeah, or orienting a ship on the sea. I don't know how to put it the best way. Yeah, you have an axis that is easy to reconstruct. You have a shaft that you turn, you have the center hole and a center hole, and you can recreate the x-axis over and over. So question is, what happens if I take that element and I'm analyzing stresses for the element being rotated? What will happen with those stresses? How they are going to migrate, to change? And this is analysis that shows, the force equilibrium, which is, if you take stress, you multiply it by area, you assume unit thickness, and you have this, the h and h, it's square dimension of the element. So what happens if I rotate the element? And they take it like a section that it's some angle phi, and I want to know how this piece that's left from the original element is going to, be kept in equilibrium by the forces that act on their surfaces. So shear, which is in the y direction, tau xy, and sigma x, they don't change for this face. But here I add, there's more surface area, and this surface area went down because I made a cut. From original h length, I went only this much. And I can evaluate, if I know, so again, I modify the angle phi, or take it as a variable angle. How are these forces going to change? And force per unit area is nothing but stress. So I said thickness is unit, and then if you multiply unit by this length, and then divide by the force that results from the equilibrium of the element, you get the respective stress. Okay, and this is what it's, well, they say h to be a cube, what this analysis does. So or as function of phi, you will end up with a relationship that is getting you the stress on the sloped part of the new wedge-like element. Oh, somebody left. I thought somebody's coming in. Okay, so from equilibrium, you get these equations that get you the stress on that incline portion of the element. And resorting to static equilibrium equations, again, you have one unmodified stress, the other one that on the horizontal surface that was is diminished because I have less length BC went from h to a smaller value. Okay, and this one which was magnified. Okay, so I can write equilibrium equations and I can solve for the unknown stress at that incline on that inclined surface, and that's a well, doesn't have a number equation, so you get to this one here that tells you the stress on an element where you begin with sigma x, sigma y, and tau xy. What happens if I modify that angle? If angle phi goes to 0, then I miss what term? If it goes to 0, this goes to 0, and so cosine of 0 degrees 1, and you can see I get just sigma x. If phi goes to 90 degrees, this is going to be 0 again, and I end up with sigma y. So I go back to cases that were like what pre-existing. So for phi equals 0, this becomes this surface. I found sigma x and tau xy, and then if phi is 90 degrees, I find sigma y and tau yx. Okay, sigma tau yx, tau xy, they are equal, but they differ by their sign. Okay, so it's important to know how tau xy, how sigma u change as I'm modifying the angle, and those correspond to what are called principal stresses. So there are angles that you can, you'll find that will maximize the sigma u, and then you'll be at another angle which happens to be 90 degrees rotated from the early one that minimizes sigma 2. Those are principal stress. Principal stresses, you're not associated with shear stress, and that's called principal element. When there's no, so as I'm rotating the element, I'll find an instance where there's no shear, if it makes sense. So I tune the element, and I'll find an orientation, an angle phi, for which there's no shear, and the two stresses, normal stresses, become maximum and minimum. All right? If I go either further forward or backwards, pi over 2 or 45 degrees, I get an element that will maximize shear stress. So there will be an angle where the shear stress is maximum. Okay, and I can evaluate it. It's given here, the equation. So what will be tau? And this is the equation that we looked at as given for the maximum shear stress theory, if you remember. And for that element where shear stress is maximum, I have normal stresses. They are equal to the average sigma x and sigma y. So yeah, we have equations that allows us to calculate the stresses, minimum, maximum, that is principal stresses, and maximum shear stress, and the corresponding angles. But there's a graphical way which engineers use to keep track of those correlations. Okay, so you see here a reference frame. This is a pretty important concept, and it takes a while to master. There are apps online. I have a spreadsheet where you can just type in sigma x, sigma y, tau xy, and draws the Mohr circle for you right away. But there's a there is a procedure that allows you to draw the Mohr circle it is. And you see I have the sigma axis and I have the tau axis. Now on the actual element, the two axes are at 45 degrees. So this is a reference frame where angles are doubled over what the part does, or over the real system, if it makes sense. So on the real element, between sigma and tau axis, I have 45 degrees. 45 degrees. But here I have, how I should put it, between sigma 1 and sigma x and sigma y, I have 90 degrees. Here they are 180. And then between sigma and tau, I have 45, and now I have 9. So how do you start? You start with sigma x, sigma y, tau xy, and you find the center of the circle. This is a diagram that you should bookmark. So you find the center of the circle by taking the average of sigma x and sigma y, and that will be the element. And then some books, they just say, okay, so and then I can get two diametral points on the circle by locating the point of coordinates sigma x tau xy, and then sigma y and tau x. And the two taus happen to be one positive, one negative. Of course, one can be positive, one negative, in case these points will mirror. Okay, but this goes further and says the radius of the Mohr circle is going to be square root of a squared plus b squared, where b squared is tau xy, which is equal to tau ix in magnitude, and then a is going to be what? Half of sigma x minus sigma y. So sigma average 1 over 2 parentheses sigma x plus sigma y, and the horizontal projection of the radius, it's the one that you say here. Okay, so A and B notations, radius of the circle, center of the circle, two diameter points. In order to draw the circle, you just put a compass and you draw and come around. Oftentimes it helps if you mirror this point and you mirror this point, because the two will be also on the circle. So you have 1, 2, 3, 4 points on the circle. It's easier to draw by hand a circle that goes through 4 points. So next page, it shows how you continue the diagram. I never refer to but it was here all the time, the original stress element. So again, you oriented with conveniently with the part, the x and y, and you identify the magnitudes and orientation of the stresses. So I have sigma x that's tensile, sigma y is compressive, and then tau xy, it's clockwise, tau yx counterclockwise. Okay, so you draw the circle again. You follow this procedure. You draw the circle, and where the circle intersects the sigma axis, you have sigma 1 and sigma 2. These are the principal stresses, the 2D principal stresses. And then the radius of the circle is going to be tau max. Okay, tau max was the square root of a squared plus b squared, but that we saw that with equation, with square root of exactly this, 1 over 2 sigma x minus sigma y, and then b was tau xy. So you saw this equation when we were contemplating the maximum shear stress as you orient the element. So useful diagrams to accompany the Mohr circle would be the original stress element, the orientation of the principal element. So when you have shear, the principal element is rotated, and you can match angles on the circle with angles of the element and vice versa. All you need to do is just double them. So I'm lowering this to where I can show you the what is called the x-axis on the circle. So x-axis of the stress element on the Mohr circle connects the origin of the circle with the point of coordinates sigma x and tau xy. Okay, so the principal element now has to be where I take in order to go from the stress element, the one with which I start, to get the principal element where the stresses are minimum, maximum, and there's no shear. I need to rotate the element by what amount? By half of this angle. Do you follow? Everybody's doing other things.
Okay, so you have 2 phi. This is the stress element on the circle. To get a principal element, I need to rotate the stress element half the angle until I match or rotate the x-axis to overlap with the positive of sigma axis. Okay? Now, to get the element where shear is maximum, you get it either rotating the principal element further 45 or backwards 45, or on the circle, on the Mohr circle, you need to rotate double that angle. So I go from I need to go 90 degrees. So this would be the principal element. X-axis, now it's in the direction of sigma max. To find tau max, I need to go half of the angle, it's visible here, or double the angle 90 degrees on the Mohr circle. Or I can go backwards. Okay, again, it says tau max counterclockwise, tau max clockwise is just a convention. Again, you have, if tau xy is clockwise, tau yx will be counterclockwise. Okay, so there are arrangements where the circle, and I need to find an example. So this will be for the 3D circle. So I follow the procedure, the origin of the circle, 2 diameter points, x-axis, and with this diagram, the Mohr circle as a just 2D circle, I'm not going to capture the actual maximum shear stress. So on the I said on one of the early questions that I asked, what is the stress in the z direction? The stress in the z direction is 0. You need to account for that in order to capture a full effect upon the material. So you will call this sigma 1, you call this sigma 2, and then you will call a sigma 3 at 0 stress. And you draw the shear, or the 3D, the full circle, by going through the 0 stress. And that's the one that's going to give you the true shear, maximum shear stress, if it makes sense. Okay? So the order of reporting principal stress is sigma 1, the largest. Sigma 2 could be 0, or the second stress, and sigma 3, the minimum, and it could be 0. Again, when you have this kind of instance with sigma 1 and sigma 2 both positive, or could be both negative, I'm on the left-hand side of the tau axis, I need to introduce a third stress in order to make full assessment of the shear stress upon the element. Okay. And this is the full 2D or 3D circle rather. So the original that you build using the procedure was the center of the circle, 2 diameter points, radius, and you know I'm including sigma 2. Draw these 2 circles. The full 3D circle is the one that encompasses the 0. Or could be some negative stress, really. If I have that system dropped to the bottom of the ocean, I have a negative compress acting on the surface, which will shift this point to the left, if it makes sense. Okay. All right. So this was for the Mohr circle and combined stresses. The book has a lot of verbiage. That's why is how much you pay for the book. That's why they're expensive. The previous edition was thinner and easier to carry. The 7th edition is smaller format, but is very thick. I like the thinner, larger format than the small format, thicker books for some reason. They pound me with emails asking for feedback how I like their 7th edition. I'm in the process of responding. I'm sorry? I did, but the lead author is probably spending too much time fishing or staying with grandkids. They ignored my feedback. Okay, so let's go back to the L-shaped piece and do the deflection analysis, because I tend to like it. It's a principal superposition and a little bit of exercise beyond what the book does. Actually, I don't need this. I need to go back to or blank this
Do I need to blanket? No, I need to go to paint and raise this. So let's do now deflection analysis. Let's see how much we can salvage of all the equations that are on the board. So I said the force, some geometry, this value I care, or formula I care about it, and I'm going to erase this to where we can do some additional drawings and analysis. So back to the original question. How much is this point going to drop under the effect of the load P of 1,500 newtons? And we're going to look at the cumulative effect of this point B moving down by some amount. I need to make this a little bit bigger. Okay, so this point goes down delta y of, or rather z of B. And this point here goes down due to, together with B, and then goes down because of the rotation of section BC without any bending. And then it goes down due to the bending of point C. Okay, so I have bending, and it's a drop by delta Z at point B. Okay, and then with it, I have the horizontal portion. So when parallel to itself, and it moves down by ZB. Again, don't ignore this. Well, it's not in the book. He's making things up. Who knows? It might be in the final. So it goes down, I said, the same amount. But then I have a rotation, a twist of section AB. So due to the twist, which I'm translating down, I have another drop. So this was another piece of, or drop, this one. So it's delta Z at C due to torsion, twist. Can you follow? So again, I have the element, or rather the L-shaped piece, and due to the force being moved at B, it just bent, and with it, this went down the same amount. But then because the force came with a twist, okay, I have down and twist. And that's this drop. And I want to make sure that this is straight line. Whichever order you take is going to be there. So this is a rotation angle theta, and theta by this equation will be B torque, which we called M at, what was the moment? MBX over shear modulus and moment of inertia. All right, and then I have the actual bending. So there's bending of this horizontal piece. So the total delta Z total is going to be delta Z at B plus what is this delta Z at C due to twist. So that's going to be this theta of the section AB. Can you help me here? We're assuming small deflections, small rotations, small displacements, small everything. So again, piece AB, and then the torque, and it produced the twist, ignoring the bend of the shorter A length piece. How much is this is going to go down? If I know the angle of twist. Untwisted, twisted, bent, and then I have bent. In addition, I have bent this for three components. the one due to twisting, how big is going to be? Okay, so remember dynamics? You had dynamics, right? So when you have a displacement on a circle, I have r, and I have the angle theta, and the arch length s is going to be what? How do you write it? So it's going to be s equals r times theta in radians. And for small theta, we measure displacement vertically, so this is also equal to the length of the arch, or length of the arch equals to the chord, proximate to the chord of S. Do you remember all these from dynamics? Oh my gosh. Yeah, that was long ago, and maybe it was a summer class, and okay, small angles, or irrespective of the angle, the length of the arch is radius on a circle, radius times the angle in radians. Now for small thetas, the S equals the chord. So you can say S approximately the chord, and it's R times theta. So how big is this going to be? Theta AB, which we're going to get it with this formula, where L is going to be just B times what? What does it go there? Well, I don't want value. We have notation. So what is going to be multiplied by? To get the corresponding movement of point C just due to the torsion. You call it CB, which is, hey, yeah, 150. You like values? Yeah, so we can use CB or A. L, I said, is going to be B here. But yeah, this is BC. So really, if you look at this figure, this is the arm, this is radius, and this is inside, the other in the hallway, and I go by theta, and I want this piece. Was it clear? How many of you understood? Again, this is dynamics. You saw this in dynamics. Maybe you saw it in calculus 2 or physics 1. A while is not an excuse, like not knowing that the speed limit is 65 and they catch you running at 85 miles per hour. That's not an excuse, right? Or anyway, and then we have the last component, which is this one. So this is delta Z at C due to bending of BC. Okay, so delta Z at B and delta Z at C bending. Is it clear? Which one here is uncharted ground? Well, I would say none, because we can use formula method to calculate this deflection, and the same equation will work to find this other third deflection, and then in between value, all I need to do is just calculate this angle of twist. So using formula method, we know the amount of deflection on a cantilever that is loaded by a force P placed at the end. This is a cantilever taken by itself. It's a cantilever with a force P at the end. This other piece is a cantilever with force P at the end. And of course, there's the twist that's added to it. So this is the middle term. So I have bending, I add them, and then the rotation, the middle term. Okay, so we had the distance L, and this is Y in the appendix, and I'm going to go to the book, welcome to Chrome, and go to appendix, and where is it? Cantilevers, and is the first one. So what is deflection at the end of the cantilever? Is right there. It's negative P. Why is that? Because it's down. Y is up. So I'm going to just write it negative P times L at power 3 over 3 EI. From, again, entry is A, appendix A20, page is 804. Okay, so let me erase this line and populate the two bending terms. So what do I write here based on this formula? Come on. Help me spare my voice. Well, let's write notations. So we're talking about deflection of this cantilever. So what is L? L becomes B. We have E and I if it's a solid bar, and which is the case. So I have I is for solid rounds. You can go to the appendix 1. So solid round bar, area moment of inertia is pi diameter power 4 over 64. Pi diameter power 4 over 64. And we also need polar moment of inertia, which is half of, or at the double pi diameter power 4 over 32. This is from appendix number 1. We've been here numerous times. Okay, so we said that this piece is going to be, and yeah, actually these are z values. We use y here, but our z is also positive up, so it'll be negative. And I can say p times b at power 3 over 3 Young's modulus times this term, pi diameter at power 4 over 64. Okay. Also going down, so this will be a negative value overall. I have the twist effect, and it will be B times, or torque is P times A over shear modulus of the elasticity in shear, that is, and then times pi diameter at power 4 over 32. And then the last one, the third term, that is, it's bending, deflection to bending of a cantilever of length now 8. So I repeat this equation. It will be P times A at power 3 over 3E times pi diameter at power 4 over 64. And this is it. Okay. So we could pull B, was this TL? What we're missing here, this is just the angle. So I need to multiply by A. Oh, I have the A, I'm sorry. So all good. I was checking, so, is it correct? PA, B, and of course, yeah, I have another A. Yeah, I was right, being wrong. So another A. So I have length of power 3, 1, 2, 3, length of power 3, length of power 3. So now dimensionally they are homogeneous. A quick verification that the equations are correct. So one thing we could do to simplify calculations with numbers will be to pull in front P and pi diameter at power 4 over 32. So I can say P over pi diameter at power 4 over 32. And then I have here b at power 3 over 3e over 2. And then plus, minus is all in front, plus I have b times a squared, b times a squared over shear modulus, and then plus a at power 3 over 3e, 3 over 2. E over 2 equals negatives. And we can calculate this now. We can put the values again, newtons in millimeters. So this will be 1500. This will be 300. This will be 300. This will be 150. And this is 150. E is that, so we need to get this into megapascals. So it'll be 200 times 10 to the power 3 megapascals. And this is 80 times 10 to the power 3 megapascals. All right. Okay. So again, 200 times 10 to the power 3. And this one, what was it? 80 rather. Times 10 to the power 3. Okay. All right. So let's see. So taking care of this parenthesis first would be 300 at power 3 plus 150 at power 3 equals everything divided by 3 divided by 200 exponent 3 times 2 equals. So I've got this plus this. And then I said plus 300 times 150 squared over 80 exponent 3 all equal, and then times 1500 over pi over the diameter is 30 at power 4 times 32 equals, and I've got negative 3.501, 3.5 millimeters. So this is the answer, which is a reasonable value. 3.5 millimeters is it's a small amount. Okay, and this was the problem. Imagine you have a cantilever sticking out, and you put a wrench and you tighten it. You know, what will happen to where we apply the wrench force? First, you can, for a wrench case, you may say wrench is way stiffer, a monkey wrench, way stiffer than the pipe maybe you tighten a cap or something. An Allen wrench? Oh, if this looks like an Allen wrench, yes. I mean, yeah, you work a stubborn hex head with an Allen wrench, although it's natural for you not to induce too much bending because you hold it to where, even if you use an extension to a socket wrench, you hold this end as you, is that right? You don't want to bend this piece. So when you work with the Allen wrench, you what? You within your palm with the fingers, you limit the amount of bending of the Allen wrench stem. You cannot explain why, but I mean, heck, if you just take the Allen wrench and put a force here, make just come out of the socket, right? You have to help it. Yeah, sometimes working with students on projects, I need to explain to them why I think something is not going to work. And, you know, it's like going from, if you're a bit familiar with writing computer code, you know, you have it in the binary code, and you need to bring it back to like MATLAB source code that you can understand. Yeah, I know, it comes with experience or playing with mechanical things. And yeah, speaking of which, don't lose. Some of you may have the opportunity, have done already. if you see, I'm talking to mechanical engineers, but when you see mechanics working on somebody taking something apart. I remember they were fixing the elevator in this building, and I could see what's on top of the elevator. There was some transmission belts and mechanical parts and also circuits. And can I take a photograph? That's one thing. But if you have a chance to just observe, they have the experience. Believe me, it's capstone. Yes, we'll have the chance to to exercise things that you've learned. But when you go in industry, nobody will let you ruin a shop or a factory or a company for you to learn engineering. You just, sit there, observe, water the flowers for the first few months or weeks, and you slowly, your responsibilities will slowly go up, or you work with people that are more experienced. Anyway, so this was a problem, and we can now, since we have, so all clear, can I erase it? You took your photographs, rely on my recording. This last one wasn't as popular. The problem is that you won't see formula method in assignments or exams, but I wish you luck with the spreadsheets. So let me erase and calculate the maximum shear stress and draw the Mohr circle. Do we still have time? 10 minutes. We can calculate the maximum stresses on top of, or a z-axis at A, on top of the pipe at A, and draw the Mohr circle and find principal stress. Let's see if we can do it quickly. I also have a spreadsheet. I'll share it with you. There's apps online. They also do Mohr circle. You just need to be careful. They, convention for shear, whether clockwise or counterclockwise, is assumed positive, but that matters less. So let's calculate tau max. Of course, it will be at A. And then let's calculate sigma max. Well, I'm saying max. It's just tau xy, and sigma will be x. And I'm going to redo the element. So again, we have x and y will be up. So essentially, we're looking from behind. Y is up, x is to the right. And we have sigma x, and then we said that, an element that, I rub in the tau xy intersects x is in the direction y is going to be this one. This is tau xy and tau xy and tau xy. So tau xy is going to be counterclockwise. This is tau yx, tau xy again, tau yx. All right. So what is? Let's begin with sigma x. I reverse it. So sigma x. What is sigma x? It's m times d over 2. We said over I. And what moment? It's the bending moment, which is p times b. So I have p times b times diameter of the pipe over 2, or the bar over 2 rather, over I pi diameter at power 4 over 64. Could use instead S section modulus, which combines the d over 2 above with this one. So what is P? We have the value. B is 3, so 1500 times 300 times half of the diameter is 15. And below I have pi 30 at power 4 over 64. And it's a positive tensile stress. We can quickly calculate it. So 1500 times 300 times 15 over pi times 64 over 30 at power 4 equals. So I have 169.76. I can call it 8. Actually, easily, this is 170, 0 megapascals, easily. Okay. And now tau xy, that's going to be torque times diameter over 2 over pole moment of inertia. The torque is going to be P times A. And we have likewise diameter over 2, and then pi diameter to the power 4 over 32. Okay, so 1500 times 150 times 15 over pi over 30 at power 4 over 32. Okay, so 1500 times 150 times 15 over pi times 32 over 30 at power 4 equals, this is 42.4 megapascals. Okay, so I have the stresses on the stress element figured out. What is sigma y? What is sigma y? Nil. We don't have a sigma y, it's 0. And likewise, sigma z is 0. Okay? So I can draw the, let's see how I can work this. Yeah. I can draw a Mohr circle with a little bit of effort in this area. So remember, we have sigma, we have tau. Man, I need a chair. So tau. And you all have the book. So instead of projecting, I'm just going to tell or open to that page. That's it's good to bookmark. It shows us how to start the Mohr circle. Page is 610 and figure is 1030. Okay, so the center of the circle, it's the average of sigma x and sigma y. We don't have a sigma y, so it's going to be 170, and we need to what? Again, this is clockwise positive. Have a sense of how big this is. So 70. I have, if I go in increments like 1, 10, 20, I need to have 17, 10, 20, 30, maybe 20, 40, 60, 80, 100, 120, 140, 180. No, 160, 180. 160, 180. Okay, and I'll try to get likewise. So average is going to be sigma average, which is the center of the circle. It's sigma x plus sigma y divided by 2. So that's 170 plus 0 divided by 2, 170 over 2. Again, I'm looking at the figure. So center of the circle O is at 85. So 80, 90 here, 85. So 85 equals sigma average. And then I need the radius of the circle. R is going to be, what does it say? It's a squared plus b squared. A squared is going to be 1 over 2 sigma x, and so it's going to be 1 over 2 sigma x minus sigma y, which is 0, squared. Plus tau xy. B is tau xy squared, likewise. So it's going to be, since sigma y is 0, this is going to be likewise 85. So it's 85 squared plus tau xy, that was 42.4 squared. So radius of the circle, 85 squared plus 42.4 squared equals, and take the square root. This is 94.988, easily 95 megapascals. Okay, so radius of the circle is 95. Now I can draw the two diametral points. Remember? So one will be sigma x and tau xy, but my tau xy is counterclockwise. So I need to show that over the example in the book, it will be a mirror point. So I have 85, 100, 120, 40, 160. Okay, and then tau xy again is 42.5. So let's try again, 20, and then 40, and 60,
and 100. So negative 20, negative 40, negative 60, negative 80, negative 100. Right? So again, 42 point will be something like this. I need more space. So 85 sigma average. So I said 42.4. So this is 50, 45, something like this, going with, okay, so this is the first diameter point. Okay? And the x-axis will go from the center of the circle to O point. I can show it in color, in red. Okay, and then I can draw the second diameter point, number 2 diameter point, and that has the coordinates of sigma y and tau yx. Tau yx is clockwise, will be up, and sigma y is 0. So the other diameter point will be like right here. It happens to be, because of sigma y being 0, it happens to be on the tau axis. This is the second diameter point. And I can extend this all right. So I have 2 diameter points on the circle, and I can add the third one, and I can mirror. I said it's easier. Please consider that when working with like freehand drawings, to mirror points 1 and 2 about the horizontal axis. So now I can draw the Mohr circle easier because it has to go through point 1 and its mirror, point 2 and its mirror. Right? So why not use the adjuvant? The university is insuring me if I fall. Okay. Will become viral. I can retire if this if there are billions of viewers of this video. I can retire. Okay, so the x-axis now is going of the element. So x-axis along the pipe, as shown, is going to be this one. The principal element has to be rotated by half of this angle. This is 2 phi. So you need to likewise you orient, look at the again of the pipe from above to the right as x-axis, and you can rotate the element, the stress element, original stress element, in the direction shown. It is counterclockwise by half that angle. So let's calculate this angle. What is this angle? 2 phi is going to be, I can get it, it's in this triangle, right? Rather easy. So 2 phi, where phi is going to be 1/2 arctangent of this piece over this piece. So 1/2 arctangent, and opposing is tau xy. I take the magnitude is 42.4, and the other one is A, which was 70/2, so that's 85. Okay, so let's see how this is in degrees. I take 42/2, rather 42.4 over 85, shift tangent, and then divide by 2. So this is 13.255, 13.26 degrees. Understood? So in order to get the principal element, I need to look at my pipe from behind, and z-axis coming through my eye, and I need to rotate the element. What amount? That 20 or 13.26 degrees. Does it make sense? So an element that's oriented at that angle relative to the original x-axis is going to have the principal stresses. And so let's see what the principal stresses now are. So I have, this is going to be sigma 1, and this is going to be sigma 2. So sigma 1, actually this is sigma 3, thinking principal elements, or the 3D circle. So this is sigma 1, sigma 3, sigma 2 is 0, and sigma 3 is going to be a negative 1. So I have sigma 1, I have sigma 3, and I can tell their values. So sigma 1 is going to be the center of the circle plus the radius. Sigma 3 is going to be the center of the circle minus the radius. So the value of Mohr circle, put in graphical form a good amount of equations that were introduced earlier. So 85, that's the center of the circle, and then minus radius, I round it to 95, and that's negative 10. So this is negative 10 megapascals. Sigma 1 is going to be 85 plus the radius, 95. And that's 180. Okay, so sigma 1, 180 megapascals. Sigma 3, negative 10 megapascal. And I can put here sigma 2 equals 0. That's, again, that's no convention of labeling the principal stresses. Sigma 1, the biggest, sigma 3, the smallest, with its sign. And it could be 0. It could be 0, sigma 3, for a circle like the one that I presented, the 2D circle that is shifted to the, or could be the other one. Okay, now the element where shear is maximum. I can go and orient it this way to intersect tau max. By the way, tau max I can calculate. Tau max, negative tau max, is going to be what? Nothing but the radius of the circle. So it's negative 80 or negative 95, and above will be tau max 95 megapascal. Okay. So what is tau max? We've got it. R is also tau max. And again, it's 95 megapascals. And if we're to draw the maximum shear stress element, well, I can go with the principal element and rotate 45, or the other way, 45, or I can go with this element and rotate it by this angle, taken half in the same direction. So this is going to be 1326 times 2, go back to the circle, and then subtract 90, that's 63 for 48, and then divide by 2, and this is 3174. So this is 2 times 31.74 degrees. Okay, so I can again work, I can draw to the left the maximum shear stress element. So you take the stress element, the original stress element, and you rotate it 3174 degrees. And I'm going to see sigma average, which is 85, all positive megapascals, sigma average. And then if I went in the direction it's shown, then this will be a negative stress that is clockwise, or counterclockwise, I'm sorry. So this is tau max. Okay? So original element aligned with the longitudinal axis of the part. Element where the maximum stresses occur, sigma 1, sigma 2, sigma 3. And then the element where maximum shear stress occurs, which is rotated 45 degrees or 45 degrees of the principal element. Again, principal element will have the axis, the sigma axis. I go 90 degrees on the circle, 45 degrees on the part.
or I can start with the original element, stress element, and I rotated. The shortest path is to go clockwise now by half of this angle. Or you can go counterclockwise, this bigger angle. In that case, these four. So essentially, it's like having a what? Looking at what was x-axis now being, rotated in upwards instead. Were you able to follow? So is the motivation clear? You find principal stresses. You can calculate a maximum shear stress that can relate with the yield strength in shear for the material and declare failure when there's combination of stress. You cannot tell, but just looking at sigma x or tau y, xy alone. What's the combined effect? And I kept on joking, in a fist fight, the punch has to be in the same location, okay? So it has to be we looked all the time at the stress in one spot. We didn't take bending stress here and shear stress below. They have to be in the same spot, okay? They don't meet the bending stress and the shear stress due to bending. They are luckily in different locations. They don't in the negative sense combine their effect. But torsion, yes. All right. This is going to be on the test on the last test on Wednesday. And the final exam is comprehensive. Has Dr. Am sent you an email? That it means he didn't. Well, I asked him to do a peer observation of teaching, and he'll most likely do watching my YouTubes. I can probably stop working already. No, still going. What have I done good to you? So I can stop recording.